everyone. My name is Jared Griffin, and welcome to the Text Mining in R virtual workshop. So first off, let's actually take a look at our learning outcomes. So after taking this workshop, participants should be able to do the following. Use R to clean text data into the tidy text format. Analyze a set of text for sentiment. Create term frequency and inverse document frequency data frames. Understand the concept of topic modeling, and finally, create visualizations for visual analysis. So before we get into the programming aspect, we have actually prepared all of the RMarkdown coding files here on this GitHub. So I can post this in the chat, or it'll be in the chat below. You can visit this page. It should look identical to this. And then if you click this green code button here, and then click download zip, you can actually download all of this code here. So just save the file wherever you would like. And then if you open up the zip file, you will have access to the project file as well as the markdown for the text mining as well as the Twitter API access. So I would, if you're following along with the workshop, open up the text_mining.rmd or RMarkdown file here. All right, so let's jump back to the presentation while you guys are downloading that. So this project does kind of use the Twitter API, so you will need access to it. If you don't have access, we created a markdown file or PDF instructions that will be linked below or on that GitHub page as well. So that'll give you good instructions on what you need to do to get access to the Twitter API. So let's jump into R and we can kind of start some housekeeping things. So I'm going to start up RStudio here. It will take a second or two. And then I'm going to create a new project once RStudio has loaded up. All right, so we can exit out of that. I'm going to go to File and then New Project. And click New Directory, then New Project. And I'm just going to call this project Text Mining, and then it'll just be on my desktop. So I'll create that. All right, that looks good. Now we can click this, or we can go to File, New File, and then click RMarkdown. Previously in the other workshops, we used R scripts, but here we can use RMarkdown. It kind of helps us to break up our work into more manageable and easier to understand chunks, as well as provide some very nice output at the very end. So I'm going to just call this text mining, and then you want to leave it in this HTML output format because that can then switch to PDF or Word. All right, so we will let that open up. Now I'm going to hide my environment as well as this console down here. And this is our RMarkdown file. And I'm going to delete everything here except for this little setup chunk. And then what we can do is if you're in this little black area on my screen, as you can see, that's just going to appear as regular text. If you want to insert a code block, what you can do is click this green kind of C with the plus right up here, and then click whatever language you want it to be in. We'll be using R, so we want to insert a new R chunk. So here we are, we have our R chunk, and now we can title this. So I'm just going to title this packages. So there are quite a few packages that we will be using today. So if you can run that very first chunk on the R Markdown file that was provided for you, this packages our Markdown section, what it'll do is it'll check and look through all of the packages you have installed. And if you don't have any of the ones we need for today installed, it should automatically install it for you. So that's just kind of a nice way to handle that. I don't get any output here because I already have all of the packages installed. To run, if you're not familiar with our Markdown, to run an entire chunk of code, you can click this little green arrow that will be in the upper right-hand corner of the chunk, and it'll say something along the lines of run current chunk. Here we are. There is the red arrow, green arrow, and while it's running, it will turn red, and you should see some progress bar alongside of your little code chunk. All right, so now that we have that, all of our packages installed, we can now load up access to our Twitter API. So I'm going to insert another R code chunk, and I'm just going to call it Twitter API. And then I'm going to copy and paste the Twitter API code chunk that is in the R Markdown. So these are my keys, so they will not work with you or for you. So you will need to get your specific Twitter API keys and that process is described in the Twitter API access HTML or PDF or R Markdown file. So we can run this as well just to make sure everything's working. And we do get our token. All right, so that's kind of all of our housekeeping stuff done. So now we can get back to our content. Well, actually, we need to do one more thing. We actually need to access our data or create our data. So what we'll be doing today is actually scraping tweets from the center's Twitter. So let's take a look at the center's Twitter really quick. So it'll load up here. So here we have the center. It appears to have 78 tweets. And we are most interested right now in the username. So we'll just kind of keep this Twitter page up in the background so that we know some information about it. All right, so I'm going to insert another code chunk and get started. So I'm just going to call this, how about data importing? So first off, we need to load some packages. So we will be using the tidyverse throughout. And to use kind of that R Twitter API, we can use a library called rtweet. There are many other different libraries for accessing the Twitter API, but as of now, rtweet is kind of the most versatile and useful one for us. So once we have these two libraries loaded, you can just type this in and run the little code chunk if you would like, or you can highlight the two lines you want to run and then hit Control and Enter. Either work. So now what we can do is actually access that Twitter API. So what we will do is use the get_timelines function that is a part of the rtweet package. And you only need one parameter here, and that's going to be the username of the center. So it's going to be essentially what is ever after the little @ symbol. So here it's going to be CPP_CCIDM, and then you can just pass that into this function. And let's take a look at what that returns. It may take a second or two because we are accessing the Twitter API. So there is some communication going along there. But as you see, it returned a tibble, which is just a table that is used by the tidyverse. So we have 78 rows by 90 columns. So that means we have 90 pieces of information for each tweet here. That's a lot. We don't want every single thing we only want a few kind of key data points here. So text will be an important one. That is the actual tweet. And we also want this is retweet column because we don't want retweets. We only want what the center is outputting directly. So now that we have this get timelines function working, let's store that into a data frame. And I'm just going to call it timeline data frame. All right, so we can now run that. It'll take a second again because we're accessing the API. All right, and let's just make sure it worked. We can just double click timeline df, run it, and we should get some output. Yes, there we go. So that's everything we want off of the timeline. We can confirm it has 78 rows, and if you look at the center, it shows as 78 tweets up here. So that is perfect. So now we've pretty much extracted all of our information from the API. So I'm going to close out of that window. And now we can do some data manipulation. So let's access that timeline data frame. And then let's start doing some piping so that we can kind of narrow down and select what we want from these tweets. So as I said before, we only want tweets that are not retweets. So we do not want the retweets. So what we can do is just use a verb known as filter and say that is retweet. We want that to be equal to false. So now if I were to run this little pipe, we can jump over to that is retweet column. And now we see we have, that's all false. So we actually only have 36 tweets here that are original center tweets. So that is nice. There are a lot of other columns we really don't care about, like tweet count or favorite count. We don't care about those too much right now. So what we can do is run a select verb and then just say we want the text column. So that's going to be that actual tweet column here. So now if I were to run this entire pipe, you see we just have one column with 36 rows. So that's perfect for us right now. Next, we actually want to give each one of these tweets an ID. That'll help us just for plotting visually and just for accessing them. So what we can do is run the cbind function, and then we're going to call this column tweet underscore ID. And then we just need to generate some numbers. These tweets are in reverse chronological order. So we need to just generate numbers that work well for that. So we want the very first tweet to have the tweet ID of 1. So I know there are 36 tweets. So I'm going to go 36:1, and that should generate numbers from 36 all the way down to 1. So let's take a look at that. All right, there's our text column. If we jump to the next column, known as tweet ID, we are successful in our ID generation. This is good. We can do a little bit more manipulation. I want to actually rename all of these, or that text column, to tweet, just for usability. So now if I were to run this pipe, there we go. We have our tweet column. And finally, there is one more thing we have to deal with. If you look through some of these tweets, you will see that a lot of them have links at the very end. So we need to get rid of these links because they will cause issues later on as we're analyzing our data. So there's a few different ways you can get rid of the links, but I have found that writing a function is the easiest in our use case. So I'm just going to copy and paste this from the Markdown file that already exists, and then I can explain it a little bit. So what I'm doing is I'm just creating a remove URL function by calling the function command here. And we'll just be passing in something, which is a string. And then we're going to use the function, which is gsub. So what this does is it looks for, in the first parameter, it looks for that, and it will replace it with whatever you give in the second parameter. And then it also asks for the data. So in our case, we want to get rid of links. So all links are going to start with that HTTP, and then it will be followed by some combination of alphanumeric characters, as well as some sort of punctuation. So this formatting here is kind of regex, which is just a kind of relatively complicated way of selecting and dealing with kind of strings. But all you need to know is that we're looking for alphanumeric numbers as well as punctuation that follow the HTTP text, and then we are subbing it or replacing it with nothing. So now that we have this function written out, we can run it, and that will store the function. And we can add another pipe, and we can pipe all of our data or each one of those text or tweets through that function. So we're going to call the mutate verb and say we want that tweet column to be the output of the remove URL function. And what are we passing into the remove URL function? We are passing each one of those tweets. So now we can run this entire pipe and take a look. Let's just try to look at that same tweet. I think it was here. We no longer see any of our links. So that means our process worked well. So you can learn a little bit more about regex just by searching it on the internet. It is fairly complex, but it is very powerful. All right, so now that we have our timeline data frame all cleaned up, let's actually store that somewhere. Let's store that into a tweets data frame. Now we can run this, and great, everything looks like it ran well. So now, if you don't have access to the Twitter API, we still want you to be able to follow along. So if you look in that RMarkdown file, there should be a commented out line of code that shows with a read CSV function, and then a direct link to a tweets.csv I created that holds essentially the exact same information as here. So you can just run this line of code and skip the rest of it, and you will get nice clean data to deal with. All right, so that was a little bit of work, but we got our data and it is nice and clean. So we can talk about the actual workshop, and starting with the tidy text format. So what is the tidy text format? It is nearly identical to the tidy data format that the tidyverse uses. That's where it gets tidy from. So for tidy text, it's going to be each variable is a column, each observation is a row, and each type of observational unit is a table. What does that kind of mean in tidy text terms? It means that tidy text is defined as a table with one token per row. But what is a token? A token is a meaningful unit of text that you can kind of define. It can be a word, sentence, paragraph, or an n-gram, which we will talk about in a bit. Finally, that process of splitting the text up into those tokens is called tokenization. So let's jump into R and let's actually tokenize all of our tweets. So I'm going to insert a new code block here. I'm just going to call it tidy text. And then we can make this a little bit bigger. There we are. All right. So there is a very nice package to help us convert text into tidy text, and that is going to just be called the tidy text library. So I'm going to run this and have it pop up. There we go. So now we can tokenize our tweets very easily through this package. All we need to do is call the unnest underscore tokens function, which is a part of that tidy text. And then it's going to ask for some information or some parameters. First, it's going to ask for our data, which is just the tweets data frame we created earlier. Then it's going to ask for our input column. Our input column here is each individual tweet, so we can just say it's going to be tweet. And then we need to also specify an output column, and I'm just going to call that word. So now if I were to run this code chunk, just look at our output, you can see we now have 1,340 rows with only 2 columns. So you can see each, or it's separated by tweet ID, but we have a word, and it's separated by each individual word. So we successfully tokenized our tweet. So let's store that into a data frame. I'm just going to call it tokenized underscore tweets. So let's store that. There we go. And let's just look at it one more time, make sure it's there. Yes, we have it, which is great. All right. So now this is cool, but so far not too much information came out of this. So let's actually try to figure out how often words show up. So just the count of the words in all of the center tweets. It might give us a better idea of what the center is tweeting about. So first I'm going to pull up that tokenized tweets data frame, and then I'm going to start a pipe. First, what we need to do, since we just have the tweet ID in Word, we actually need to count all of those words. So we can use the count function or the count verb. And what do we want to count? We want to count the word, and which is our word column. And then we can also specify sort can be equal to true. This will just sort that column for us. So if we run this pipe, you see we have our word and we have our n, or our count. You will notice it does drop the tweet ID because we're just looking at the all of the tweets as a whole. We will look at individual tweet counts later. All right, so we now have our word counts, which is great. I want to rename that n column to count. So I'm going to call a rename function and then just say I want a count column to be equal to n. So this is just renaming that n column to count. Makes our lives a little more simple and easier to understand. Next, we are plotting. So I'm just going to, we're plotting a chart. So I'm going to say that I'm going to filter out all of the words that have less counts than, how about 5? This is because there are over 451 unique words throughout all of the tweets, and fitting 451 words on a plot is going to be nearly impossible to get everything looking nice in this case. So we'll just filter those small, not that important words out. Next, we also want to kind of reorder the data frame. So we're going to call the mutate function, and then we are going to say that that word column is going to be equal to the output of this reorder function. And we're just we are reordering it by word and count. So now if we take a look at this, we now have everything sorted by count in descending order. So that is nice. And we only have 49 words to plot now. So the next little chunk, I'm just going to copy and paste from the existing code because it is a relatively standard ggplot. So now if we were to take a look at this or run that entire pipe, we can see the count of the words in the CCIDM tweets. So you just see the most often word that shows up at the very top and so on. So here we have a lot of words like the, to, and a. Research is a good one. For, of, center is another good one. At. But if you notice, a lot of these words, they're not really important for our kind of analysis. Pretty much any text you look at, it's going to have a lot of count of the and to and. So these words aren't really important. So we can actually deal with them. Those words are actually known as stop words. So let's jump back to the presentation real quick. And we can take a look in the lower right-hand corner for how we will be dealing with these stop words. So there are two kind of pieces of the puzzle to dealing with stop words. One is going to be the stop words lexicon. And a lexicon is essentially just a dictionary of predetermined words. So in our case, the stop words lexicon just is full of words like the and to and so on. So what we can do is use the anti-join function to kind of compare all of the words in our tweet and all of the words in the stop words. So as you can see in the lower right-hand corner, we're getting rid of all of the stop words and we're getting rid of where the tweet words overlap with the stop words. So we're just getting all of our tweet words that and excluding the stop words. So you can see in the lower right-hand corner, we keep the green and we will get rid of the red. So we can go ahead and do this fairly easily in R. What we can do is actually modify this existing pipe. So I'm going to add it as the first, or the very first kind of hole it's going to go through, or the first pipe it's going to go through. So we will use that anti_join function, and then all we need to do is pass in the stop words. So the stop words is actually given to us already. We don't need to generate them. It is automatically given to us. So we will, if we were to just look at this tokenized tweets and then with the anti-join of the stop words, so just that first little chunk, oh, we apparently don't get anything. So let's just run this entire chunk. Oh, we cannot find the function. How odd. That was just working well. All right, that was a little weird one, but we're working well now. So we did use that anti-join to get rid of all of the stop words. So now, if we were to look at the words in all of the CCIDM tweets, we have kind of more juicy or meaty words. If you were to think of it, stop words are kind of like fluff and things you really don't care about. But these words are kind of the meat of what the text is about. So we can take a look at them briefly. So we have like research, center, that makes sense. We're all about research at the center, and obviously we'll be using the center's name a lot. We have join and register. So it looks like maybe we are trying to have people go to a lot of events and so on. You can just kind of look at our most often words used. All right, so that is a pretty nice way of visualizing how words or how frequent words show up in all of the tweets. But there are a few other ways. So we'll take a look at one. We'll take a look at the word cloud. So I'm going to copy and paste this chunk from the existing code, but we will be using the library GG word cloud to generate a word cloud. So we can just run this entire chunk. If you notice, all of the anti-join and counting logic is identical to above. So all we're really changing here is the ggplot. So let's run this entire chunk. All right, and then now we get an output. So the more common words are going to be larger, and you can specify them to be a different color, and less frequent words will be smaller. So this is a much kind of more intuitive and pretty way to share just basic word counts from all of the tweets. So you see right smack dab in the middle, we have research, nice and big, which is the most important word that we found previously, or sorry, most common word we found previously. All right, so that was just looking at some basic analysis of just pure counts of words in the tweets. But we can do much more interesting things with kind of text mining. So let's jump back to the presentation, and we can take a look at sentiment analysis. So when humans hear words, they can actually kind of understand or infer the emotional intent of those words. But computers really can't do this. If I were to say, like, I hated that, most people would be able to understand that that is kind of negative, and but computers, when they see something like hate, they have no reaction to it because, you know, they're computers. But there are some ways we can deal with this. We could manually go through and say that each word is negative or positive, but that would be very time consuming. And thankfully, people have already done this for us, and we are allowed to use these. So these kind of essentially books or sets of words are known as lexicons, which I had mentioned earlier, which are essentially just dictionaries full of words. So there's kind of three general purpose ones we can briefly look at today. The affin, Bing, and NRC lexicons. So before we jump back into R, take a look in the lower left-hand corner where it shows the tweet, interjoin, and lexicon. So not every word in our tweet is going to be in the lexicon. Like my name, for instance, probably isn't in any of these lexicons because there's no real sentiment or emotion behind my name that researchers would have outputted. So what we can do is look at the tweet data, or look at all of our tweet words, and then look at all of the words that are in the lexicon, and then we can just see where they kind of overlap and just keep those words. So in the lower left-hand corner, we'll just be keeping where they overlap. So we can actually take a look at that really quick. I'm going to insert another R code chunk, and then I'm just going to call this sent for sentiment analysis. First, we can actually take a look at some of these lexicons. So let's take a look at all three. I'm just going to copy paste here. So we have the affin lexicon, we have the Bing lexicon, and then we have that NRC lexicon. So this is actually how you get access to these lexicons, is by running this get sentiments function, and then passing in the name of the lexicon that you want to use. If you are running these lines of code for the very first time, you may need to open up your console, and they may ask you to agree to some licensing agreements, essentially saying that you're going to be using it for personal or for research purposes, and they ask you to cite them if you use it for research purposes. So you can just, I think, type in 1 to agree or something along those lines, and then you are free to use them. So let's take a look at that first lexicon, the affin lexicon. So you see, if we run that get sentiments function, we get a tibble that has about 2,500 words. And for each one of these words, it gives a numerical value for it. So abandon is a kind of negative word. It has negative sentiment to it. So that is given the value of -2. Abhor has a value of -3. If we were to find a positive word like admired, that has a value of +3. So this lexicon just helps us to get numerical approximations for sentiment. The Bing lexicon is a little bit more simple, but it has a lot more words. So it has about 6,700 words. But what happens in this lexicon is that it just gives a positive or negative sentiment output. So abolish has negative sentiment, but accolades has positive sentiment. So you kind of lose a little bit of resolution there. Get sentiments, or the NRC lexicon, it shows as about 14,000 rows, but what's happening here is for each word, different emotions are given. So abandon has 3 different emotions according to this lexicon, which are fear, negative, and sadness. So there aren't really 14,000 words here because there are a lot of repeats. But it does allow us to see a lot of the different emotions that are associated with each of the words. So that is great. It's nice we don't have to do any manual tagging because that would take forever. So now we can actually use these to take a look at how our tweets sentiment are. So what we can do is access that tokenized tweets data frame. And then since we want to look at the each tweet, so each individual tweet's sentiment, we need to actually group by the tweet ID. So if we were to run this, you can see it says groups tweet ID. So all of these words are grouped by their tweet ID, which is what we want. Next, we can actually run that inner join function that we talked about earlier. So the way you kind of do this is you call the interjoin function, and then you can just pass into it the get underscore sentiments function, and then you pass into that the name of the lexicon you want to use. So we will use the affin lexicon here because it does give us that numerical kind of approximation. So we can run this entire pipe, take a look at it, and there we go. So you can see we have our tweet ID, we have our word, and we have our value or our sentiment. So as you can see, there's only one word in the 36th tweet that overlapped with that lexicon, with that affin lexicon. So it does cut down on the amount of words that are in each tweet that we're analyzing. So let's continue here. What we can do next is actually figure out the mean sentiment for all of these tweets, or for each tweet. So what we want to do is just find the mean value here of the value column, and that will give us a just the average sentiment for that tweet. So I'll call the summarize function, and then I want to create a column called mean sentiment, and the formula for getting the mean of the tweet sentiment is just going to be the mean function. So we're just finding the mean of this value column. So now if we were to run this little pipe, we get an output. We have our tweet ID and we have our mean sentiment. So that's perfect. So we have the average sentiment by tweet. So once that has been done, It is more or less some relatively simple ggplotting. So I'm just going to copy and paste that from the Markdown file. And now we can run this. Oh, we don't get num tweets. That's because I made it a little more fancy in the Markdown. So here we go. All right, so now you can see we have our mean sentiment by tweet. You see our tweets range from 1 to 36 because we had 36 tweets, and then we just have a numerical value for sentiment. So overall, it looks like our tweets are certainly more positive than negative, which is good. We don't want to be having negative emotions being portrayed in our tweets. So that is good. But you will notice it appears there are two tweets, 3 and 4, that don't have any sentiment attributed to them. So let's take a look at those. So let's take a look at tweet number 4 first. So what I'm going to do is just access that tokenized tweets data frame, and I'm just going to run a filter saying the tweet ID I want is going to be 4. So now we could take a look at this tweet, and it's just the tokenized tweet, so it's nothing too special for us right now. But what we can do is run that inner join function again with the get sentiments function as well, and then that affin lexicon, and we can see where or how many words overlap in the 4th tweet and the affin lexicon. So let's run that. And you can see here our output is 0 rows. So that means 0 words were found in both the affin lexicon as well as the 4th tweet. So if we again look at that bar chart, you see we can't really say the 4th tweet has a mean sentiment of 0. All we can really say is that it has no sentiment according to the affin lexicon. So that is an issue when you're dealing with small amounts of text, such as a tweet. There could just be not enough words to fall into any of the lexicons. So let's see if that issue is the same with tweet number 3. We could do that just replacing 4 with a 3. Take a look at that. Nope, we get some words for tweet 3. So let's take one more look at that plot, because it appears we do have some negative tweets. So like tweet 28 shows as negative according to the affin lexicon. So let's look at tweet 28 to see if that's true. So we can run that. And you see here, there are 2 words that pop up in the affin lexicon, which are growing and miss. And it appears miss is giving us that -2 value. So let's just take a look at that tweet. We can read it out loud, see what's going on. Oh, that is just the tokenized tweets. There we go. Here's our tweet. So it says, our full 6-part virtual R workshop series is uploaded to the YouTube channel. It has a list of playlists. So this tweet is pretty obviously not negative to us. But when we're dealing with this small amount of words in a tweet, there can be some kind of false negatives. So that is something to keep an eye out for. As you get more text and more words to tokenize on, these errors become less frequent. All right, so this plot was a pretty nice way to look at how all of our tweets have different sentiment, but there is a different, kind of more pretty way to do it. I'm going to copy and paste this from the Markdown file. What we will be doing, we're going to be using 2 libraries here. which are the Reshape and Word Cloud libraries. So as you may have guessed, we are indeed making another word cloud here. So let's just run this entire chunk of code. What we're doing here, this is all the same as what we're doing previously, but this word cloud or these comparison clouds require a matrix to function properly. So we need to use this acast function. And then we can pass all of that data into the comparison cloud function. So now if we were to look at our comparison cloud for all of our tweets, we get a red for a negative sentiment and green for positive. And we can see kind of some of our words that may come across as negative. So if we're looking at them, we see missed and miss are two very large ones. But that's generally when we're talking about, oh, if you missed the workshop, you can see it on our YouTube channel. Issue and crisis, those could be negative, but injustices as well. But break and fall, those really aren't negative in the context we are looking at it, because we're probably talking about fall break, which arguably is very positive. So those are some kind of false positives we get when we're just looking at individual words. But we can also look at the positive words like successful, thank, happy, and so on. And those are all nice and positive and happy. All right. So we can now go ahead and jump back to the presentation. We can move on to term frequency and inverse document frequency. So what we were doing previously was just finding just the normal counts of the words in a tweet or overall, but we can get a little bit more sophisticated than just that very basic analysis. So what we can do is create two things, but they eventually become one, which are the term frequency and inverse document frequency data frames. So term frequency is just how frequently a word occurs in a document. So that's just how many times the word appeared divided by the total amount of words. So that is relatively basic. But next, we have the inverse document frequency. And that is just the implementation of Zipf's law, stating that the frequency a word appears is inversely proportional to its rank and importance. So what they're saying here is the more often the word appears, the less important it really is. So we can kind of see that already. We saw that the appeared the most often, but really it's not that important to us at all. So here is the formula for how you can kind of find the inverse document frequency for an individual term. It's just the natural log of the number of documents divided by the number of documents containing that term. So let's jump back to R. It can look a little complex, but thankfully we have some nice libraries that will help us out. So I'm going to create a new R chunk here, and I'm just going to call it TF-IDF. All right. So now what we can do is let's just create that standard term frequency we found or we just looked at. So that's just the number of times the words appear divided by the total amount of words. So let's access our tokenized tweets data frame. And then we're going to run that count again. Word is what we're counting, and then we want it to sort. This is identical to what we have been doing before. And then we are going to rename the column identical to what we did before as well. I'll just copy paste it. But now we want to call the mutate function so we can create a new column. And we're going to just call that total. And we want to get the total of all of the words. So let's just see what our data frame looks like before we mutate it. So we have this count column. So the total of all the words is just the sum of that count column. So now we can take a look at this output, and you see it has all of the totals. They're the same. We could have calculated total off on the side, but this will work just fine. So now we have that total and we have that count per word. Most of our work is done here. We just need to call one more mutate function. So I want to call it term frequency. And the way we find term frequency is just count divided by the total. So now if we were to run this, you see we have our word, we have our count, and we have our TF column or term frequency. And you can see we get values for the, to, and, for, and so on. But this is a relatively basic way of dealing with this. So what we can do instead is use the power of these already existing functions to make our life easier. So I'm going to just copy and paste just up to that rename function. And instead of calculating everything manually, we can be a little bit lazy here, and we can use a function called bind underscore TF underscore IDF. And you can see it is from the tidy text library. And it's going to ask for 3 things. Well, 4 really, but we're already giving it the data, so we don't need to worry about that. It's going to first ask for the term. So in our case, the term is just going to be the word, and then it's going to ask for the document. So that kind of depends what you're working on, but in our case, the document is going to be the tweet. So each individual tweet is a document. So we can specify it's going to be tweet ID. And then finally, it's going to ask for n, or the count of the term. And we already figured out the count by running that count function. So we can just pass in that count column. So now if I were to run this, oh, we get an error, which is just not fantastic. Let's see. That is because I did not include the tweet underscore ID. So this bind TF-IDF had no idea that that tweet ID existed. So now if we were to run this, there we go. We get our TF-IDF matrix. So here you can see words like and. It has a relatively high TF, so it pops up quite often. But if we were to look at the IDF, we see it is weighted very low versus a word like team that shows up much less overall. So this again will kind of weight words that show up less frequently as more important. So you can see here in this TF-IDF column, a word like team is pretty high up there, but a word like the has a very small value. All right. So let's take a look at this a little bit more, but it's kind of boring to just look at a data frame like this. So let's actually get to visualizing. So what we can do is actually first store this into a tweet underscore TF underscore IDF data frame. You could call it whatever you'd like, of course. There we go, it's stored. So now we can access that. So we will access the tweet underscore TF IDF and then start some piping on it. We only want a few columns out of that. So we can run that select function. So we want the word, we want the tweet ID, and we want the TF underscore IDF column, and then the count. So this will allow us to work with our data frame a little bit easier. Next, we want to look at it grouped by tweets. So we want to compare tweets. So we can run that group by function and say we want to group by the tweet ID. Next, what we want to do is we're going to just select the top 5 words from each tweet. What we're doing overall, the goal for this visualization is to create a word cloud for each tweet that shows the top tweets or the top words per tweet. So in order to do this, we need to use the slice_max function. And that is just going to allow us to take the top however many words you want for each tweet. So first we can say we want it to be ordered by the count of each tweet, or the count of each word. And then it's going to ask for an n. So that's just the number of words we want. Let's actually grab 6 instead of 5. And then finally, we can give it this with ties parameter. And we'll set that to false because we don't want ties. We'll just take the first 6 words excluding ties, because that'll give us more than we want. Next, we don't want to look at all 36 some odd tweets. So let's just run another filter function here. And let's say that the tweet ID needs to be less than 6. So that should give us tweets 1 through 5. Next, it's just going to be a relatively standard ggplot. And we will be faceting by the tweet ID. So that's going to give us, that should give us 5 different word clouds. So let's run this. There we go. So now what this is, they are word clouds, or essentially just 6 different words for each tweet. And these are the words that appear most often in each tweet. So this is just looking at the count of the words. So if we were to just look at these tweets by their counts of words, we can see the first tweet says CCIDM account followed new, so maybe a new account. Number 2 is teams accepted phase, so teams got accepted. We can kind of understand what those are about, but tweets like tweet number 5, where it says 2020 center from this, we don't really understand the context here because most of these are just kind of stop words. So what we can do is, I'm going to just copy and paste this entire chunk. Instead of ordering it by count, we can order it by that TF IDF column. So that's where the words are weighted kind of by importance. So let's run this entire chunk here, and we can compare those 2 different word clouds to see how things work when we're just looking at the counts versus when we're looking at the TF IDF scores. So if we were to look at that first tweet, so this one is going to be the TF IDF. So it says, welcome, regular account, Twitter updates follow. That's not much more different than the first tweet, but all the stop words are more or less gone, and these are just the more kind of meatier and important words. Number 2, phase, team, accepted, pretty similar to number 2 according to the count importance. But when we look at tweets like number 3, according to the TF-IDF, the important words are injustice, against, racial, proud. So we get a much better understanding of tweet 3's topic versus just looking at the count. Because according to the count, we're against something, but they really don't show those important words. It's best demonstrated with tweet number 5. So according to the TF-IDF, November, globe, around, this, announce, in Korea are all very important. But if we were to just look at the pure counts of the words, we would get something, we would get this, 2022 center from this. So that really makes no sense. So that's why we kind of use that TF-IDF to weight words on importance. So the more important words kind of bubble to the top, and we can get a better idea of what the tweets could be about. All right, so that will be good for kind of term frequency and inverse document frequency. So we can now move on to our next section, which is going to be kind of relationships between words. So to kind of understand relationships between words, you first need to understand n-grams. So n-grams, n is just going to be a number. It is essentially how we are going to split up our text. So our text for the workshop has been each individual tweet. So far we tokenized it, but we only used the unigram or the 1 gram. So in this example, we have the sentence, "The cat ran away." And if we were to just look at the unigrams, we would see that we have 4 of them. So the cat ran and away. So that is just looking at each individual word, and we don't really get the context of the entire sentence. So we can understand that it has something to do with a cat and something to do with running, but we can't really say that it is the cat that ran. It's fairly obvious here, but when you're dealing with larger strings or much larger data, it's not obvious. So we can actually look at bigrams or tokenize the sentence through bigrams and take a look at that. So bigrams can give a much better context for what's going on in a particular text. So here the bigrams are the cat ran, and ran away. So here we could say fairly easily that the cat ran. And then where did it go? It ran away. So that grabs some more broad topics in the sentence. Finally, we have trigrams, which are splitting it up into chunks of 3. So we have the cat ran, and then we have the cat ran away. So that last little trigram actually captures the entire essence of the sentence, where we're saying the cat ran away. So depending on what you're using kind of text mining for, you will figure out what you should tokenize, or how many words you should use for when you're tokenizing. It is good to keep in mind that if you notice here, every time we increased 1 with the gram, we lost 1 kind of entry. So first off, the unigram had 4, you can think of them as rows. The bigram has 3 rows, and the trigram only has 2 rows. So it does kind of reduce your overall amount of text or rows and entries. You can have as many grams as you want. You could have an 80 gram, but you'll kind of have to evaluate if that would ever be effective for you. We can now jump into R. So let's do that. Thankfully, with the data we're dealing with, and most likely the data you're dealing with, computing is relatively cheap. So all you have to do to experiment with different numbers of n-gram is just by specifying the n value to be different. So we'll kind of demonstrate that here. So first, let's actually create the bigrams. So we'll access that original tweets data frame, and creating bigrams or trigrams, it's more or less the same. So what we'll have to do is run the not in nest, unnest tokens function. It's going to pop up for me. There we go. So we're going to run that unnest tokens function, which we looked at the very beginning of this. And we're going to have to kind of specify some things. So it's going to ask for an output. So let's say our output is going to be bigram. Then it's going to ask for an input. So that's just going to be your document, which in our case is just the tweet. Then it's going to ask for the token. And we can just specify that the token is going to be n grams. And then finally, what we can do is actually specify our n, which that's where n gets its, or n grams get their n from. Since we're doing a bigram, we're going to have our n be 2. If we were doing a trigram, it would be 3, and so on and so forth. So if we were to just look at when n is 2, so create our bigrams, let's take a look at this. You see, we have our tweet ID, and then we have our bigram. So here it says, join us on Friday, March 5th. And you kind of see this weird pattern show up where it kind of takes that previous word. But this is nice for helping us to find relationships between words, because now we can kind of tell in context that if we're using Friday and March, if those show up together a lot of the time, we can say there is some sort of relationship between them. But all right, so let's store this into a, into a tweets underscore bigram data frame. So let's run that. There we go. We don't get an output. That's fine. And we'll take a look at that one more time. And if you notice, we have some entries or some bigrams that say for the, and those are stop words. So just like previously, we need to get rid of these stop words. Since we do have bigrams, it is a little bit more complex than just that unigram. But the good news is that from converting from bigram to trigram and so forth, the kind of removal of stop words is more or less the same process. So what we need to do to actually remove these stop words is first separate this bigram column into 2 columns. So we'll run the separate function and then pass it our bigram column because we want to separate that column. And then what we can do, it'll ask for essentially where do you want to store these 2 words. So I'm going to use that C or standard combine operator, and then I'm going to give it 2 column names that I want it to create. So I want it to create a word 1 column, and then we can give it a word 2 column. Very creative. But now we also need to give that separate function one more piece of information. We need to say what to separate on or where to split. So what we can do is we see that all of these are separated by a white space. So what we can do is say SEP, or the separator here, is just going to be a white space. And now if we were to run that pipe, we can see our output. Oh, let's do that to see our output. And here we go. We have word 1 and word 2, all nice and separated for us. So next, what we can do is run a filter function. And what's happening here, so we're going to say not word 1 and use this really interesting in operator, which essentially looks through a list. But you can look at this independently. It's a very interesting operator. And then we need to look for all of the words that are in the stop words kind of data and that actual word that we're looking at. This entire little line is just a complex way of writing that anti-join. But the same thing is happening here. It's just a lot more complex instead of just calling that original anti-join function. So the reason we're doing it is because we need to filter both word1 column and word2 column. So we can just copy that filter function or line of code and paste it. And instead of word1, we can just look at that second column. So that's why it's kind of easy to scale this up to however many words you have split this into, because you can just copy and paste this as much as you would like up to however many words you have split. So now let's take a look at what this output should give us. All right, we get our tweet ID and then we get our different words, and this is good. So we now have bigrams that get rid of all of the stop words. So it's not too bad to deal with. So let's store that in the tweets underscore bigram data frame. So now what we can do, just like before, we're essentially going to rerun all of the analysis we did previously with the unigram, except it's going to be with a bigram. And there are just very slight differences for each, or for switching between unigrams and bigrams. So I will be copying and pasting a little bit here because the code is so repetitive. So first off, let's actually do the counts like we did before, just the plain and simple word counts for the bigrams. So what we can do is we can say we want to count word 1. We also want to count word 2. And then we can, again, say we want it to be sorted. So now let's run that, see what it looks like. And here we go. So we see digital marketing shows up the most often. So that's the bigram that shows up the most often. Then CCIDM, research, then research seminar, and so on. So this shows us just our most frequently used bigrams. All right. So let's actually store this into a bigram counts just data frame. So there we go. That is all stored away. Again, counts aren't that interesting. So what we can do is instead create that TF-IDF matrix. So here we go. I'm just going to copy and paste this from the Markdown because it is just the exact same thing as what we were dealing with before, except for unnesting tokens, we're saying we're using the bigram and we're setting n equal to 2. And then for the count, we have to specify that it is the bigram. And then for the bind TF IDF function, again, just passing in the bigram. But all of this is all the same. So now if we were to take a look at this, we now have a TF IDF of all of our bigrams. Oh, let's get rid of this head so we can actually look at everything. And here we go. So we see grouped by tweet ID, we have our bigram, our count, its standard term frequency, as well as inverse document frequency, as well as our TF IDF. So you see all of these kind of have the same TF IDF score, but as we scroll around, we see we get different T. Is nice, but just like before, it's boring to look at it in a kind of matrix like this, or I guess it's a tibble. So it's kind of boring. So what we can do instead is use some interesting libraries known as iGraph and ggraph. So here we go. Those are the libraries. I just copy and pasted it. And what we can do is we actually need to do a few steps to create a kind of visual look between all of the related words in the center's tweets. So first, I need to create a bigraph variable. And then I'm going to access that bigram underscore counts variable. and I'm going to pass it through a pipe. I'm going to first filter. I want n to be greater than 2 just because we don't want to have however many bigrams popping up. So what, 1300? We just want to filter to where they appear more than twice. That will make our lives a little easier for plotting. And then next, we need to call this graph underscore from, there's a lot of them here, from underscore data frame function. So what this will do is we'll kind of set up the chart for us. It will be a little bit more clear once I actually generate the plot. So now we can run this and we don't get an output, so no errors. That is nice. Now we can pass this bigram graph into the or the ggraph function. So we'll pass it in, so it'll be by graph. And now we need to specify some parameters. So I'm going to say my layout is going to be FR. You can, again, mess with these layouts to kind of figure out how you want them to look. But we're kind of using a networking type layout. So we need to add some parameters to this graph. In this case, it's the edge, the point, and then a text. So now if we were to run this, hopefully it runs on the first try, it does. Now we get a kind of map that shows us how our bigrams are related. And you can kind of mine some information from here. So you see my name pops up, Jillian's name pops up, as well as Kaylin's name. And also you see the Friday, November 13th has shown up. So it can kind of recognize that these words were used in conjunction a lot. We see Cal Poly as a bigram, and as well as the time. So it sees that we used 1 and 2 p.m. a lot together. It also recognizes that we use, for Jenny, we apparently called her the director a lot, which makes sense because that is her position. So we would have referred to her in that way. So this is just a nice visual way to see how some of your words can be related. It's much nicer than looking at a kind of boring TF-IDF data frame. All right. So this was all very nice, but let's take a look at what it could look like with trigrams. So again, the process is identical. So I'm going to just insert a new code block, and I'm going to specify this as try for trigrams. And I'll be copying and pasting a lot here just because the process is identical. You see, instead of bigrams, we're just saying trigram, and we're saying n is equal to 3. And we have to have 3 of these filter statements because we have 3 words. Next, we can find the counts for all of those words. So let's just take a look at what that looks like. So you see our trigram, we have CCIDM Research Seminar, Insights Data Industry, and so on. So these are just the standard counts, identical to what we did with bigrams, except now we have 3 words. Next, we can create our TF-IDF, except again with trigrams. So let's take a look at our TF-IDF. Here we go. It just has 6 rows because we're looking at the head, but again, same process. Finally, we can run that same iGraph and gggraph and compare it versus the original. So let's run this entire chunk. And again, this is the exact same code, just slightly different variable names. So now we can take a look at our trigrams and just we're looking at the counts here. So the trigrams that pop up most often. So we have things like CCIDM Research Seminar, we have Vikings Cruises and our guest speaker. I think we also have, is that maybe Enhance, and then Industry, Data, and Insights. So it sees or identifies these kind of trigrams as popping up a lot. But there are overall a lot less data points than with our bigram. That is because we're dealing with text data here. So when we chunk it up into trigrams, we get a lot less rows and data to work with. So you will kind of need to experiment with what you should be separating or how many words you should be splitting into. But again, you saw it was fairly easy, fairly computationally cheap to see the different effects. All right, so there we go. We mined some information from both bigrams and trigrams, which are pretty much everything you will be looking at. Keep in mind, as you are deciding between which n-gram you're going to be using, you need to look at the kind of topic you are trying to do research on or data mine. If I was, let's say I was looking for job positions that include the term data science, if I were to just use a unigram, all I would see is data and all I would see is science. So I wouldn't really see that those words ever kind of overlap. So I would probably use bigrams if I were looking for a phrase like data science. Just like you would probably use a trigram if you're trying to look at something like CCIDM Research Seminar. So it really does depend on what you are going to be analyzing. So your kind of literature review will help in that context. All right, let's jump into our final topic, which is topic modeling. So topic modeling just seeks to kind of figure out what our document is about. So for us, we will be looking at the LDA or latent derelict allocation, which has two main principles, which are every document is a mixture of topics and every topic is a mixture of words. A common example is like you are reading the front page of the news. There'll probably be two broad topics there, maybe politics and the market or the economy. So for politics, you might see a lot of words like re-elect or vote or policy. And for the economics or the market topic, you will see words like topic, or sorry, not topic, words like budget or stock or price or something along those lines. So each words or each topic is a mixture of words. It can be fairly complex, as you can see it from the plate notation below, but packages like the topic models and text mining package make it much, much easier for people like us to deal with it. So let's jump back into R, create a new R code block, and I'm just going to call this TM for topic modeling. So what we can do is load up our libraries. So library, first we will be using the topic models library, as well as the TM or text mining library. All right, so in the Markdown, I actually made it a little bit easier for anybody to kind of change and modify. So what I did is I specified the number of topics, so you can easily adjust this. And then also the top n to get. So that is essentially just the top amount of words you want to get for each topic. So for the tweets we're going to be looking at today, I'm kind of using my best judgment, and I'm saying there's probably going to be about 3 topics in across all of these tweets. And we'll just look at 10 words from each of those topics. So what we can do to get started is we need to access that tweet TF-IDF because that is what is used for LDA. So we will access that TF-IDF, then run it through a pipe. So first, we need to run the anti-join function and pass it through the stop words. That is, again, just to get rid of our stop words because they don't add anything to our analysis, really. Next, we need to run the cast underscore DTM function. So what this does, you can see here in this little blurb, it says it turns tidy 1 term per document per row data frame into a document term matrix. We need a document term matrix because that is what the LDA function requires. So first off, it's going to ask for the data for this cast DTM function. We already gave it the data because we're using the piping operator. So we can first specify the document. So our document is going to be the tweet ID. If we were doing the book, it would be, if we were looking at books, it would be book titles. So it's whatever your document is. Next, it's going to ask for our term. And in our case, the term is simply the word. And finally, it's going to ask for a value. And we can just look at the count here. So since we're using this tweet TF-IDF, we are just looking at unigrams here, which is fine for our purposes. So let's run this. Let's see what happens. All right, we get a DTM or a document term matrix. We get 36 documents, so that's 36 tweets. And then we get 332 terms or 332 words. And it gives some sparsity information that we aren't too terribly worried about right now. So next we can add another pipe to this, and we can just create our LDA model. Very easy. You just use the LDA function from the topic models package, and you specify k to be equal to your number of topics. So I already specified that number of topics variable up here. So you could just as well put a number here, but to make our lives a little easier, we can do this. All right, so now if we were to run this entire little chunk and see what that LDA function is outputting, we see we get an LDA VEM topic model with 3 topics. Great, just what we want. So now we need to store that model because otherwise it's not very useful if we don't store it somewhere and use it. So I'm going to store this into a tweets underscore LDA variable, and that looks like it's working well. Run the tweets underscore LDA again just to make sure. Yep, it's still popping up. So next, if we're trying to actually use that LDA topic model, this tweets underscore LDA variable isn't too helpful because when we run it, we just get this kind of blurb saying what the variable contains. So what we need to do is actually call a function called tidy from that tidy text library and pass it that tweets LDA. And now if we were to run this, you see we get a topic, we get our term, and we get our beta. The beta here is going to be the per topic, per word probability. So it's essentially the probability that the word will appear in the topic. So if we were to look at, let's just look at that team topic, or sorry, team word, we see that for topic 1 and 2, the probability that it's in these topics is essentially 0. This number is just so small. It could be considered 0. But for the third topic, it's still pretty small, but it is just so much larger than these other probabilities. So we can say that team will most likely belong to the third topic. You can kind of see across other terms, they could be a little bit less spread out. So data, their probabilities are much closer than the team term. So we can say we probably use data across all three of these topics more or less the same amount of time. So yeah, now that we have it are these terms grouped by topics and their probabilities, we can visualize it and make our lives a little bit easier. Because looking at topics and terms and probabilities in this format is overwhelming and not the best way to do it. So what we can do is let's actually store that output somewhere. I'm going to call it tweet underscore topics. And let's run that. There we go. So now it's stored in the variable. What we can do is we want to just get that first 10 topics, or sorry, 10 words for each topic. So let's set that up right now. So let's access that tweet underscore topics variable. Then we can add a piping operator. And now we need to group it by the topic. And then we can just use that top n function and say we want to just get the top n to get. This could just be a number, but for adjustability, I set it as a variable up here. So top n to get as the numbers to get. And then it's also going to ask for kind of what column do we want to look at to get the top 10 of. And that's going to be the beta. So we want to get the top 10 terms with the highest probability. All right, next we can use another piping operator, and we actually need to ungroup this because we no longer need it to be grouped by the topic. And finally, we can arrange all of our words. So we can arrange it based off of topic. And then we also want it to be in descending beta order. So I can do that by just hitting this negative and then specifying that beta column. So that should sort it by topic as well as beta in reverse or in descending order. So let's take a look at this. And we get our output. So we have our beta. Looks like we're going from large to small, which is great. And we're also grouped by topic. So there we go. This is nice. Let's store this somewhere. Let's store this into tweet topics top terms. Why not? There we go. And now that we have this, again, kind of ugly and hard to look at in a data frame like this. So we can actually visualize it and get some very nice results to interpret. So what I'm going to do is first access that tweet topics top terms variable, set up a piping operator, and we do need to just run one mutate function here. So I want that term column, I want it to actually be reordered. So we can just call reorder underscore within, and then I want it to first be ordered by the term, then the beta, and then the topic. So we could look at this really quick. There we go. We get our term, topic, and beta. But next, all we have to do is just use a fairly standard ggplot with faceting on the topic. So we should get one plot for each topic that we can interpret. So let's run this. And there we go. So now we have our first topic, we have our second topic and third topic, and we have on bottom or on our x-axis the beta probabilities, as well as our terms on the y-axis. So let's try to interpret these. This is where your domain knowledge will kind of come in handy. So I feel I know the center pretty well, so let's see if I can interpret these topics. So for the first topic, we get marketing as our first term. Then we get center, digital, research, e-commerce, and we get our guest speaker down here. So I would have to bet this is when we had our kind of more professional marketing guest speakers for the center. For the second term, or second topic, we get the research as our first term, and that is a pretty large first term. So we can take a look. We get CCIDM, students, seminar, Friday. So I'm betting this is going to be all of the tweets pertaining to the research seminar or anything involving research with the center. And finally, for our third topic that was kind of found, we have data as our largest term, and then join. So right there, I'm kind of thinking maybe it's the workshops, because join, we want students to come. And then we get insights, and here we go, we have workshops down here. So I would say topic 3 is going to be tweets involving maybe the R workshop series or any other workshop or event we are promoting there. All right. So let's jump back to the presentation. I'll just briefly mention some quick resources. First off is the tidy text mining book I used, which was fantastic. And then next is just the Twitter developer application link if you want to access the Twitter API. All right, so let's take a look at our learning outcomes again. So after taking this workshop, participants should be able to do the following: use R to clean text data into the tidy text format, analyze a set of text for sentiment, create term frequency and inverse document frequency data frames, understand the concept of topic modeling, and finally, create visualizations for visual analysis. All right, thank you very much.